number 14. Here we go. Here it is. Oops. Okay, guys, if you're doing your homework between 4 and 5 a.m. on Friday morning,
Definitely not.
I will be fast asleep. No, you're probably asleep. All right, so here it says, consider the following hypotheses test. Okay, so tell me, that's not 14. Here we go. Consider the following hypotheses test. Is this a one or a two-tailed test? Two. Okay, so it says, the null says mu equals 22, and the alternative is mu is not 22. A sample of 75 is used. The population standard deviation is 10. Compute the p-value and critical values. And state your conclusion for each of the following. Use alpha equals 0.01. I want you to do all 7 steps. Okay? So you're going to do it for A, X bar is 23, and if you have time, B is 25.1. So 7 steps.
It'll be
B.
longer.
So in A, right, so the claim is mu is 22. Okay, the claim is that mu equals 22. And you tested for mu is 23, and you should not have been able to reject the null hypothesis. Because getting 23 is quite likely. It will happen more than 38% of the time. So in B it says, what if you got an X bar of 25.1? Is that different enough? So I'm going to go through it with you and see if this is to help you kind of collect your thoughts. So the step 3, right, is just have these written out. So that's not going to change. Step 4 is alpha. Not going to change. Step 5, my proof stays the same, n is greater than or equal to 30, and sigma is given. Okay, but now I have a different z-score. 25.1 minus 22 divided by 10 over the square root of 75. What is this test statistic? What is it? 2.68. Okay, that is the z-score. That is telling you that this number is 2.68 standard deviations above this number. Is that different enough? Is that statistically significantly different enough that you are able to reject the null hypothesis? So the critical value method, we need to know alpha and that it is two-tailed. So this is not going to change. You guys did that, right? You came up with 2.575 and negative 2.575 because this has got, right, this is alpha is split between two tails. These are your critical values. So in step 7, with the critical value method, what am I comparing to what? Yeah, I'm comparing my test statistic to my critical values. My test statistic is 2.68. Where does that fall in my graph? Up here, doesn't it? 2.68 is out over here. So my decision would be reject the null hypothesis that mu equals 22. Because I got something far enough away that I don't believe them. I got 25.1. That difference is statistically significantly different enough. For the p-value method, I need to know that the test statistic is 2.68 and that it's a two-tailed test. 2.68 negative 2.68 is always easiest to look up the negative. Okay, so negative 2.68 has an area to the left of 0.00. I think I was doing the math in my head, that was helping me remember what number it is. I think that's right. So this gives me a p-value of 0.0074. The probability of getting this number, when I take a sample of 75, if this is true, it will only happen 0.0074 of the time, or 0.74 of 1%. Again, it's very unlikely to have happened by chance. My step for the p-value, I still reject, and the reason I reject is because my p-value is less than or equal to alpha. If my p-value is less than or equal to alpha, I have enough evidence to reject the null hypothesis. I started the Learning Center back in the mid-2000s. I forget if it was 2006 or 8. It was part-time. I got a little bit of funding. I didn't work full-time. I didn't have a classroom. So what I did was it was open from 8 to 10 in the morning because there was no class in this one room, and from 4 to 6 at night. Okay, I used to run it those 2 hours. 8 to 10, 4 to 6. I used to have a piece of paper where you signed in. I didn't have all the tutor track, right? I had a piece of paper where you signed in. When you was quiet, I'd sit at my desk and I would enter everybody's name and when they came in and when they left on an Excel spreadsheet. And at the end of the semester, I sent that information to our institutional research. And I asked them to do a study between, and my goal when I opened the Learning Center really wasn't to help the really bright students, it was to help the struggling students. It was to help those who have F's and D's to become C's. Did I get students who were B's and wanted to become A's? Yes. And did I get people who had 96% who wanted to become 98? Yes, I did. But I really opened it to help the students pass the class and be successful. And so I sent it in, and I did it for a couple years. I had some more data, and it consistently showed that my students who came for tutoring were more successful. And I didn't even want them to have a higher GPA, because there are some students who just get it. They just get accounting. They don't need to go to the lab. They just get it. They never go in there. So I wasn't going to say my student's going to have a higher GPA, because I start with the students who need help, right? So, but sometimes, quite often, the people who go for tutoring, their GPA is higher than those who don't go in. And so I collected all this data, and after 2 years, that's how I received funding for this to be a full-time, open full-time. And I got a classroom before we had this building and in the other building. Because I could prove, not only did it prove, but the difference was statistically significant. That it wasn't didn't happen just due to chance, right? And I could show it consistently through the time. And so how you can use data to obtain funding for things. That's what we used to get that there. Because it didn't used to be there. And when it was there, it was part-time for a couple of years. Okay. All right, so people have questions about this before I move on. So it's all going to follow this same pattern. Everything we do. Yes, Josh?
So the p-value, anytime the p-value is less than alpha, you reject.
Yeah, that's your guiding principle. So we're going to use the same method now, but now we're going to talk about when we can't prove this. When step 5 cannot be proved, okay, and you can't use a z-score, you have to use a t-score. Okay? Otherwise, the approach is going to be exactly the same methodology the whole time. Okay, so I'm just going to show you with a t-score, and I'm going to do a proportion, but we need to kind of move through this. So, all right, a state highway patrol periodically samples vehicle speeds at various locations on a particular roadway. The sample is used to test the hypotheses that mu is less than or equal to 65. Is this a 1 or a 2-tailed test? Left or right? It's a right-tailed test. Very good. Because I can only prove them wrong if I get something higher, right? Okay, so the locations where the null is rejected are the best places for them to put radar traps. At location F, they took a sample of 64 vehicles. They got a mean of 66.2 with a standard deviation of 4.2. Test the hypotheses with alpha is 0.05. Okay, so in this case, N is 64, X bar is 66.2, and S is 4.2. Not sigma, because it says a sample of 64 vehicles shows a mean of 66.2 with a standard deviation of 4.2. It doesn't say it's the population standard deviation. Okay, and then alpha is 0.05. Okay? So, they told us the null. If the null is mu is less than or equal to 65, what is the alternative?
Greater than 65.
Greater than 65, and alpha is 0.05. Okay, everybody good? Okay. Tell me if I get going too fast. Proof. There is no proof. The only proof that could apply when you have S instead of sigma is what? N is greater than 100, right? That's the only one that doesn't need sigma. N is more than 100. Do I have N more than 100? No, there's no proof. Therefore, I have to use a t-score. T-score is a punishment or a reward? Punishment. Okay, T is a punishment. Calculated the exact same way as the z-score. What did you get when you did your sample? You got 66.2. What is the hypothesized mean? 65 divided by the standard deviation over the square root of n. Okay, so that gives me a t-score of 2.286. We do z-scores to 2 decimals and t-scores to 3 decimals. Is everybody good with me? There's really not much difference so far. You all good? Okay. P-value method and the critical value method. We'll start with the critical value method. What do I need to know? I need to know alpha is 0.05 and it's a right tail. I put all 0.05 in the right tail. Agreed? What is this z-score? So what is the area to the left?
0.95.
That's what I need to look up in my booklet. Tell me what that z-score is. Thank you. 1.6, the one that's right in the middle between 1.64 and 1.65. Yes? That's your critical value. If that's all you had to do, what is step 7? What is your decision? Where does it fall? What do you compare your oh, wrong. Oh. Woo. Yes, it's a t-score. Oh, goodness. It's a t-score. Look. So you do what? How many degrees of freedom?
63.
What is the area to the right? And this gives you a t-score of?
1.669.
Ah. No z-score. Naughty. Didn't earn it. It's a reward. The z-score's the reward, right? You didn't earn it. That is your t-score.
Why am I not getting 1.6?
I don't know. Let me see. You're looking up 005, I bet.
Jesus, I am.
I know all the mistakes that what people have to do. All right, so what is my decision? Hmm? Reject or not reject? Right, why? Because my test statistic is over here at 2.286, isn't it? This is little end is the rejection region, not this big part. The little end is the rejection region. Reject the null hypotheses that mu is less than or equal to 65. If I reject the null, I must think that the alternative is true. Mu's greater than 65. I'd write set a radar trap at location F. Because if I think this is wrong, I've got to think that the mean's more than 65 and people are speeding. Right? Agreed?
Agreed.
Right. Let's do the p-value method. What do I need to know for the p-value?
T-score?
That t is 2.286 and that it's a right tail. Agreed? So I want to know what's this area here. It's a little trickier with a t-score. When we're looking up z areas on z-scores, we have so many z-scores to pick from negative 3.59 all the way up to 3.59, right? We have hundreds to pick from. That's not the case with t-scores. I've got 10 to pick from. So if you look, you have to go to degrees of freedom of 63. Okay, and you look along that line and you're looking for 2.286. Okay, so you should see that when you're looking along, the closest numbers you see are 2.097 and then you see 2.387. Do you agree?
Yes.
That's what you see. And you know it's in here somewhere, don't you? In between there and there. So what you're going to write is you're going to say that the p-value is more than 1% but less than 2%. Because it's in between here and here. Now the silence. All right, I'm going to move on. There's a practice question, but I'm going to move on. Oh, maybe I'll do it. How about I'll do it? Cynthia, just to set it up for you. Yes.
What would you do if your alpha was like in the interval that you got?
But if it was the exact number, right? So if your p-value is less than or equal to alpha, you reject.
Okay. So like if in that situation, if alpha was 0.02, then you would reject?
No, because I've said my p-value is less than 0.02.
Oh,
Because
but it was like-
if my test statistic was 2.097, and I know it's exactly 2%, I would reject it if alpha was 2%.
Okay.
What's the next question, 28? So just to set one up for you, this says a shareholder group in lodging a protest claimed that the mean tenure for a CEO was at least 9 years. A survey showed that the mean was 7.27 with a standard deviation of 6.38. Formulate hypotheses. Okay, we're gonna do all this stuff here. Let's do this. So with this question, N is 85. It says that in part B. And the X bar they got was 7.27, and the standard deviation 6.38, and alpha in part C says 0.01. Okay. So they want to know they said that they believe step 1, mu is at least 9 years. The opposite of which is less than 9 years. So the equals goes in the null, and this is 9. Right or left tail test? Left. Okay. So step 5, there is no proof. When you've got S, N has to be more than 100 in order to use a Z. So I'm going to use a t-score, okay, and my t-score would be the sample mean minus the hypothesized mean divided by the standard deviation over the square root of 85. Okay, this will give you, so these are the hypotheses that we came up with. This will give you, okay, gives you a t-score of negative 2.50. That's the t-score that you come up with. So for the critical value method, you have to, your alpha is 0.01, it's a left tail. You need to know that this is a negative even though you don't have negative t-tables. Okay, so we go to degrees of freedom of what? 84. We go to 0.01, and what is the t-score? Okay, you should get 2.372, but know that you're looking up area to the right, and so you've got to put a negative in front of it if it's to the left. Okay. What's your decision? Reject or not reject? You're going to reject. Okay, you're going to reject because your negative 2.5 is down in here. Okay? You're going to reject the null hypothesis, which says mu is greater than or equal to 9. The shareholders who claim that are wrong, that the mean is not greater than or equal to 9. For the For the p-value, okay, you can't look up negatives, you're going to look up positives. We're going to look in here. Along 84, we're looking for 2.5. What is it between? It's between 0.005 and 0.01 because in the table, when you're looking up here, you get, this one is 2.372 and this is 2.636. It's somewhere, it's more than this, but less than that. Okay? Couple more things. Okay, so we're going to do, when do I do proportions instead of means?
Categorical.
Categorical data. Okay, so when I do categorical data, I have to do proportions. It can be a left tail, it can be a right tail, it can be a two-tailed. The test statistic for step 5 is your sample proportion minus your hypothesized proportion divided by your standard error. Notice that the standard error is using the hypothesized proportion. Comes from your step 3. Okay, you prove a z-score by doing n times p is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5. This says for Christmas and New Year week, the National Safety Council estimated 500 people would be killed and 25,000 injured on the nation's roads, and 50% of the accidents would be caused by drunk driving. They took a sample of 120 accidents, and it showed that 66, and I think your notes say 67, but I changed it to 66 because 67 gives you a repeating decimal. And so it's much easier math if we don't want to make it all about how we put the math in the calculator. So make that 66. And use this data to test their claim at alpha's 0.05. So step 1, they're claiming that P is 0.5. The opposite of that is what? Is not 0.5. Which one is my null?
First one.
The first one, because it's the first one? No, because it has the equality. Step 4, write down alpha. Step 5, calculate your test statistic. But first, make a proof. You can only use z-scores with proportions. You cannot use t-scores with proportions. Okay, they become binomial questions. What is my sample proportion? What is my p-bar? I went and gathered data. What's my sample proportion? It's 66 divided by 200, which is 0.55. Right, that's what I got when I went and did a test. What's that?
Where'd you get 200?
Oh, sorry, 120. Sorry. 120. It's 0.55. 66 divided by 120 is 0.55. It looks like they're wrong, doesn't it? They said 50% will be caused by drunk driving. I did a sample, I got 55. It looks like it's even more than 50%. But is that difference statistically significantly different or not? So you do 0.55 minus the hypothesized proportion divided by the standard error. Oh. N is 120. What is that? What is that z-score? Okay. So that gives you a z-score of 1.1. Okay, that's your z-score, 1.1. Your critical values. It's a two-tailed test, alpha's 0.05. So you split it between the two tails and you will look it up and you will see that your critical z-scores are plus and minus 1.96. What's your decision? What is your decision? I do not have enough evidence, right, to reject the null hypothesis, which is P equals 0.5. I could write, although it appears that more than 50% crashes are due to drunk driving, the difference is not statistically significant. Okay, if I did the p-value, right, this is 1.1 and it's a two-tailed test. If I look up negative 1.1 in my tables, there you go. Now what I get 0.1357 in each tail. So I get 0.2714. It's quite likely to have happened by chance, right? All right. So do your homework on chapter 9. Chapter 10 will bring in confidence intervals again, and hypotheses testing again for two populations, okay? Have a good, please clean your boards.